Today we're going to prove some ideas about general vector spaces and how we can develop the idea of a coordinate system. To begin, let's prove theorem 1.13, which reads as follows. Any n-dimensional vector space V over the field F is isomorphic to the vector space F to the n. We prove this by the following. If V1 to Vn is a basis for V, then by the mapping theorem, there's a linear transformation T from F to n, from Fn to V defined by T of delta J is equal to Vj, in the sense that the standard Kronecker delta basis vectors of F to the n are equal to, get sent to the jth element. By the mapping theorem again, the linear transformation T is injective since the image vectors are linearly independent, since we said Vj, the set of Vi's were linearly independent. And we see it's surjective since the image vectors Vj span the entire vector space, since we have their basis. Hence, the linear transformation is isomorphism between the vector spaces because it's a injective and surjective map, i.e. a bijection when viewed as a map. Therefore, we consider that the vector space F to the n for field F is not only a simple example of an n-dimensional vector space over the field F, but is a standard model for any such vector space. The choice of an isomorphism T from V to F to the n for a vector space V over field F can be viewed as a coordinate system in V, for it permits any vector V in V to be described by its image. T of V is equal to x equal to the set of xi's within Fn. So it can be described by the coordinates xi within F. Recall that xi are like your scalars, so you can think about this as a sequence of numbers, xi, that describe your vector V. So a very easy example of this is if we consider the vector spaces of polynomials over with some coefficients in some field, we can, the natural isomorphism is by simply selecting those coefficients, and we see those coefficients form a string of numbers that describe the vector, so you can think about this as the coordinate for the vector. A coordinate system for a vector space V is determined by the choice of basis for V. And since there are a great many bases, there are also a great many different coordinate systems for V. It is clear, though, that if s, t from V to Fn are any two coordinate systems for vector space V, then T is equal to us, where U is equal to Ts inverse, from F to n to the F to Fn, which is an isomorphism of that vector space F to the n. However, conversely, if S from V to Fn is a coordinate system for the vector space V, and U from Fn to Fn is an isomorphism of the vector space F to the n, then T is equal to Us from V to F to the n is also a coordinate system for the vector space V. That is, consider U to be some map from Fn to itself, so an isomorphism of some kind. You can compose this in natural ways with transformations from V to F to get other ways of considering the coordinates of V. For instance, if you have some sort of looped field, in the sense that if you add 1, eventually it'll come back on itself. It's a finite field in some variety. Then you see that shifting the coordinates up by 1 is an isomorphism Fn to the Fn, but will provide a completely different coordinate representation of any vector, and therefore is a different coordinate system. In general, for many purposes, it is sufficient just to consider the vector space F to the n, rather than the abstract vector spaces over the field F, since some general properties of finite dimensional vector spaces can be proven by simple calculation for the vector space F to the n. That is, if you can prove it you simply make an isomorphism from V to the F to the n, prove it with a simple calculation F to the n, and then take the isomorphism back to prove whatever result you want to prove. With that, we're done, and we're going to consider some ideas about linear transformations between these natural coordinate systems next time. Thank you.